My name is Kirsten Thayer, and we did our physics experiment testing the effects of gravity on objects in freefall. And this was prepared for our CSUSB Physics 2000 lab final. And my lab partners are Amanda Renburg, Sean Atkins, Jackie Bravo, and Mitzi Ramirez. For a brief introduction into our experiment, it was conducted to demonstrate the effects of gravity on an object in freefall, as well as an attempt to visualize the acceleration of gravity, which is defined to be negative 9.8 meters per second squared and is denoted by a lowercase g. This value is negative because it acts in a downward direction. All objects on Earth are affected by this gravity. And we will be measuring the time that it takes for objects to fall from a measured height and comparing this value to the accepted value of the acceleration of gravity on Earth. After you have done your review of the videos, you're going to input your time data into a Google Sheet or Excel sheet in order to complete the calculations and create data visuals. So here is a quick visual of the experiment that we completed.
So with a theoretical background, as you know, the gravity of Earth is a net acceleration towards the center of the Earth that an object experiences from gravitation. Gravitation is the national phenomenon where all things with mass or energy are drawn to one another. Earth has its own gravitational pull. It's from its magnetosphere, which is very unique to Earth. That's why other planets have differing gravities, and the rate of acceleration varies depending on the latitude and surface of landscapes. However, the value widely accepted is 9.80665 meters per second squared. This value means that an object falling increases velocity to 9.8 meters per second for each second it falls, defined by the International Bureau of Weights. Because we have the magnetosphere, it protects us from also solar flares, and it keeps gravity the way it is for us.
For our procedure, you're first going to want to establish a measurable height and temporarily mark this on your wall. You'll be repeatedly dropping an object from this height and measuring how long it takes to hit the floor. We used a measured height of 5 feet or 1.524 meters. You're then going to want to set up your video device in a way that it records the entire process of the object falling from the measured height. It is important to have both the drop and the moment it hits the floor, so everything needs to be within the frame. You're then going to begin your trials. We did 10 trials because we felt that was sufficient enough to calculate the acceleration of gravity. And after you've completed these trials, you're going to review the slow motion videos of each trial. You're going to be seeing the exact moment that it leaves your hand and the exact moment that it hits the floor in femtoseconds. So for an example of this, from our height at least, the time value should have been around 0.55 to 0.56 seconds. That value, when put into the calculation for acceleration, ended up being around 9.8 or 9.9. Then you're going to have each group member do a total of 10 trials with an object. We did a total of 4 objects. So in order to get all of that data, we had each group member participate and put it into a sheet that we could all review.
In our experiment, in order to calculate gravitational acceleration, we needed to determine the height in meters and measure how long it takes the object to fall and hit the floor in centiseconds. We wanted to determine if weight affected our acceleration value, so we each did 10 trials, each of 4 different weighted objects. We used a slow motion video on our phones to measure the exact time the object began falling and when it hit the floor. So does object mass affect acceleration of gravity? And can we demonstrate that the acceleration of gravity is 9.8 meters second squared through an at-home experiment?
So now our experiment list continues, or experiment. Our ruler or measuring tape is what we used to measure the height. Could either be a yardstick or a ruler, one or the other. 2 is a video device capable of slow motion, a smartphone or tablet. One or the other could work. Different weighing objects. We used 4 different objects, which we ran through 10 times in our trials. A calculator determining the acceleration. Then we have our Google Sheets, which we use to visualize our data, to input our values, and create a graph from it. We will be also covering the in-depth procedure of our experiment in the next couple slides. So now we get to our calculations. Our calculations, we will be determining the acceleration by using the kinematic equation, which is delta x equals v0 times time plus 1/2 times the acceleration times time squared. So VO, because it's being dropped, is the initial velocity is 0. It's starting from 0. T being the seconds used in time for our video. The delta x will be the height measured, and in our case is 1.52 meters. How we found out the acceleration of gravity provided in our next example was 2 times delta x divided by t squared, which equals a. 2 times the height, delta x is our height, divided by time to the second power, which equals our acceleration of gravity.
Raw data through the seconds, and even here you can tell there's a very big difference. We have Mitzi, who had a 56-gram object, and she had acceleration of 5.29. Me, Amanda, had an object that was 362 grams, and our acceleration was 3.34. That was funny. Wait, 3 had grams of 1,905.1, which was Jackie. Her acceleration was 2.49. Then for Kristen, she had acceleration of 9.99. We found there was a discrepancy between the group members' data for time measurements for each contributed with our own experiment. For our respective accelerations, there's a lot of different ones, as you can tell. These were the averages resulted in acceleration of gravity of 5.28 meters per second. This does not prove the acceleration of gravity is 9.8. Explanation improvements will be explained in the upcoming slides. We did demonstrate the object mass does not have an effect on gravity when acceleration versus mass was charted. It's clear there's no correlation of our data. For the results are staggering instead of an upward or downward trend.
Here we have a graph showing the average acceleration, which was measured in meters per second squared, versus the mass that was measured in grams. Here we see 4 points, each indicating the different objects. Each object had a different weight. Here we see that they are all on different spots, so there wasn't a trend line. If the mass of the object had affected gravity, a trend line would have occurred. Therefore, mass does not affect gravity. If the data we collected was more precise, the 4 objects would have fallen in a straight line at 9.8 meters per second squared.
For clarification, our results technically demonstrate that the gravities of the objects was affected by their mass, but with no correlation to heavier or lighter masses. This resulted in the seemingly random scatter plot with no trend. A demonstration of no effect would result in a horizontal trend line at 9.8, as shown below.
All of our group data, we did not demonstrate the acceleration of gravity at 9.8 meters per second squared, since one out of the 4 trials measured an acceleration of negative 9.8 meters per second squared. We can reasonably conclude these results were based off of erroneous data / experimentation, since we know that G equals negative 9.8 meters per second squared through the known law of gravitational acceleration. However, we were able to conclude that it would not affect the gravitational acceleration on Earth. So there was no correlation between our different weight objects. Each of the objects should have fallen at the same time.
All right, so our improvements and comments. The largest inconsistencies were found between the different group members' time measurements and the object's fall. Since we are currently doing distance learning, each experimental trial was completed separately. One way to improve this experiment would be to do the experiment in person together so our group members can better collaborate and we can correct any mistakes we have. Another method to improve the experiment would be putting the video into an app, which can further slow down the video, and we're able to record it in centiseconds instead of milliseconds. So even small fluctuations in time measurements was enough to not demonstrate the correct reading of our acceleration.
And that concludes our presentation of the effects of gravity on an object in free fall. And here is a slide with all of our sources. Thank you.